In this video, we will review how to solve for empirical formulas, how to turn those empirical formulas into molecular formulas, and then how to solve for the formula of a hydrate using the same method. It's a little bit different, but it still uses the same method. Okay, so an empirical formula is a reduced formula. It just shows you the ratio of elements in your compound. And the way we determine the empirical formula is we'll use percent composition values. And those values specifically come from mass spectrometry data, and that'll be our last set of notes in this unit. So for example, P2O4 is a molecular formula, or the actual formula of a compound, where if I reduced it, so this 2 and this 4 could be divisible by 2, I would get PO2, and that would be the empirical formula. Sometimes the molecular formula and the empirical formula are the same, so let's talk about water. H2O can't be reduced anymore to have a whole number, and so that is your empirical and molecular formula. So sometimes that happens. Our steps are going to be converting all of our percents to masses, if we're given percents. Sometimes we're just given masses, and so we might start at step 2, which would be converting those masses to moles. Sometimes even we're given moles, and so we might start at step 3, where we take all of our moles that we just solved for, and we looked at which one is the smallest, and then we divide everything by that smallest one. And then step 4 would be multiply by whole, and this is only sometimes. Okay, so this example says, what is the empirical formula for a compound that is 21.2% nitrogen, 6.10% hydrogen, 24.3% sulfur, and 48.4% oxygen? So our first step, we're given percent, so we will do percent to mass. So I'll take 21.2% nitrogen. I will convert it to 21.2 grams of nitrogen. I'm given 6.10% hydrogen, and I will convert that to 6.10 grams of hydrogen. I'm given 24.3% sulfur, and I will convert that to 24.3 grams of sulfur. I'm given 48.4% oxygen, and I will convert that to 48.4 grams of oxygen. Okay, so I have done percent to mass. My next step is going to be mass to moles. So I know the molar masses of all these guys. Won't be too bad. And molar mass of nitrogen is 14.01 grams of nitrogen for every 1 mole of nitrogen. Some students may say, well, why is it 14.01 and not 28.02 for diatomic nitrogen in 2? And the reason why is we use our diatomics, our Brinkelhoffs, our bromines, our iodines, our nitrogens, chlorines, oxygen, fluorine, hydrogens, when they're all by themselves. And since we have a compound that is all of this, that means that nitrogen is not actually all by itself. And so it would be not correct to do diatomic nitrogen. So I get 1.51 moles of nitrogen. Molar mass of hydrogen is 1.01. Molar mass of sulfur is 32.06. Molar mass of oxygen is 16.00. And I get 3.025 moles of oxygen. Okay, now what I'm going to do is I'm going to look at step 3, and I'm going to look at all my moles that I have, and I want to divide by the smallest one. And so when I look at all these moles, it looks like sulfur is the smallest one. So I'm going to divide everything by 0.76. And when I do that, I get 1.99. I get 7.95. I get 1. I get 3.98. And we're not going to need to multiply by whole for this specific problem. Okay, so these are the numbers. And a good rule of thumb is that if a number after you divide by small, if a number is within a tenth of the next whole number, so 0.1 within the next whole number, you can round to that number. So this 1.99 will be 2. This 7.95 will be 8. And this 3.98 will be 4. And so my formula is going to be into H8SO4, and I'll give you a moment to figure out what that formula is. This is ammonium sulfate. Okay, now I want to do an example with molecular formulas, and I'll go through the steps here. The first step is you're going to determine the empirical formula, okay? So do everything, percent to mass, mass to mole, divide by small, and multiply by whole if necessary. Then you're going to get the molar mass of your empirical formula. And I said you need to get the molar mass of your molecular formula, but you're going to be given that. And then you're just going to compare them and see how many times can the smaller one, the empirical formula, go into the bigger one, the molecular formula. Okay, so what I want you to do is you can either follow along. I'm going to go pretty quickly through example 1, or what I'd like you to do is pause the video and get the empirical formula, and then we can talk about the molecular formula. So I'm going to go through this quickly. So you can pause the video, get the empirical formula, and then fast forward ahead till you see where I've got the empirical formula. Okay, and then you can play it again. Okay, so I got the empirical formula. That's C4H6O. And what I want to do is I want to get its molar mass. And so we can abbreviate molar mass, MM, big M, and I get 70.10 grams per mole. Okay, so what I need to do is I need to compare that to whatever this formula is, its actual molar mass, and it tells us that the molar mass of this compound is 140. So what I can do is I can use this formula where it specifically tells me that I'm going to take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula, or I can just think about it as 140 grams per mole is what I need. Right now I have 70.10 grams per mole, and I can see how many times, and you probably can already see the answer, that we get 2. And so what does that mean? That means I'm going to take 2 times C4 H6O, and so my molecular formula, which is the actual formula, is going to be C8H12O2. Okay, one more example before we get to hydrates. And on this one, you can pause the video and get to after you divide by the smallest one, because in just a second, that's where I'm going to end up. So pause the video, do percent to mass, do mass to moles, divide by the smallest, and then resume the video. Okay. So what we have going on here after you divide by the smallest is we have these numbers, 2.67, 2.66, and 1, and they're not within 0.1 of the next whole number. So this is where we've got to look at this number, and we've got to say, are these halves? Are they thirds? Are they fourths or quarters? And I look at this as a fraction, and this is 2 2/3. So if I want to get rid of this fraction, I just need to multiply by the denominator, which would be a third. So I need to multiply everything by 3. And when I do that, I get 8, 8, and then 3. And so my empirical formula is C8H8O3, but I want the molecular formula. And so what I'm going to do is I'm going to get the molar mass of this, and I get 152.16 grams per mole. The problem tells me that the molar mass of this compound is 152, so I can be formal about it and say, okay, I'll take 152 grams per mole, and I'll divide by 152.16 grams per mole. Of course, there's a little bit of rounding here, and I get 1. So my molecular formula, and this is totally fine, this happens often, not always, but often. The molecular formula is going to be C8H8O3. They can be the same. Okay, so in your previous chemistry class, you should have discussed hydrates. Hydrates are a little bit different, and what they are is it's going to be some sort of ionic crystal where water is included in the crystal structure, but water is not permanently bonded, okay? And so what that means is when we heat it, the water is going to evaporate because it has a low boiling point, and most ionic compounds have boiling points maybe 1,000 degrees Celsius to maybe even 1,500 degrees Celsius, and it just depends on the ionic compound. And so we're not going to boil the ionic compound. And so what we get is if we heat a hydrate, the water will evaporate, and what will be left is the stuff that we didn't get hot enough to actually boil away or to evaporate, and so that's called the anhydrate. The prefix a or an means not. So that is not the hydrate or without water. So because water is not permanently bound, we use a little dot, and that means that we have copper sulfate as our ionic compound, and that'll become our anhydrate. But we have these waters, 5 of them specifically bound, and when we heat it, that's what this arrow above, or gosh, that's what this triangle above the arrow means. The water will turn into gas, and our anhydrate solid will be left behind. Okay, and so when you determine the formula of the hydrate, we're going to use the same steps, but instead of breaking the compound into each element, we're just going to break it into anhydrate and water. Okay, so that's going to be important. And then on a couple of these examples, we'll be asked to get the molar mass, and that's totally fine. That's something we should be able to do. And what we do is we get the molar mass of our regular compound. So here we have copper sulfate. That's 159.61 grams per mole. And what a lot of people do is they just add 18.02 because that's water. But that's incorrect because we have 5 waters. So we really just need to multiply that by the correct number of waters and then add them together. And then that'll give us the correct molar mass. So we're going to do a couple examples here. Hydrates are something that we want to be good at just because once you get the hang of it, it won't be too bad. And it's like as the freest points you could think of that could show up on a test, quiz, or even the AP test. Okay, so what we have is this student, and this student's going to take 1.082 grams of nickel 2 sulfate hydrate. So it's got some number of waters if it's a hydrate. And we're going to heat it in a crucible or an evaporating dish. And after heating, we have the anhydrous material. Okay, so this is my anhydrate. And I just want to know the formula of the hydrate and the molar mass of the hydrate. So here's how I kind of organize any of these problems. Is I'm going to say we have nickel 2 sulfate, so that's NiSO4, and it's a hydrate, so we have some number of waters, and I don't know that number. I'm going to heat it, and assuming that I've done the lab correctly, where I heat until a constant mass to indicate that all of the water has likely been removed, I'm going to get my anhydrate, and then I'm going to get my water vapor. And the problem tells me is I'm going to mark this up a little bit, that this is 1.082 grams. And this guy is 0.596 grams. Okay, if we look back to what I highlighted, this is probably the key idea here, and that's why we have a little key there, is instead of breaking the compound into each element, so we're not going to break it into nickel, sulfur, oxygen, and hydrogen, we're going to break it into the ionic compound, the anhydrate, which that's this guy, and water. Okay, so I need a value for water here. And the way I'm going to do that is I'm going to take 1.082 grams minus 0.596 grams. And in that process, I should get the amount of water according to the law of conservation of mass. Okay. So then we're going to do percent to mass, mass to mole, divide by small. And we'll never have to multiply until whole with hydrates. Okay, percent to mass, that's been done. We have masses, so we'll do mass to moles. We have 0.596 grams of NiSO4. And we have 0.486 grams of water. There's 18.02 grams of water for every 1 mole of water. That gives us 0.0269 moles of water. And the molar mass of nickel sulfate is 154.75. And that's for 1 mole of nickel sulfate. And so I get 0.00385 moles of NiSO4. So I've done mass to moles. I need to divide by the smallest one, which that should always be your anhydrate. And when I do that, I get 1, and I get 6.99. That's within a tenth, so we can call that 7. And so my formula is NiSO4, 7 H2Os. And then to get the molar mass of that, what I'm going to do is I'm just going to use, be a little bit clever, as I already got nickel sulfate, so that's 154.75. And then I'm just going to add 7 waters to that. And when I do that, and maybe instead of writing 7 waters, I should do 7 times 18.02. I get 280.89 grams per mole. Okay, so I want you to try this next one. I'm not going to go through it. I'm just going to give you the answer, so you want to pause it. And if you want to see work, that work is posted online. So pause the video, try this number 2 out. I'm going to move on to number 3. Okay, now this will be our last problem here. And this is kind of how you want to think, because you're going to have a lab where I'm going to give you an unknown hydrate. And you've got to create your own data table, procedure, and all that. But you kind of want to set it up like this, and I think you'll be the most successful that way. So, number 3 says, a student is assigned the task of determining the number of moles of water in 1 mole of this magnesium chloride hydrate. So how many waters are there? The student has this data from this table. So they have their dish, their crucible, and then they put stuff in it, and then stuff is heated and blah, blah, blah. And so what question A says is, it says, explain why the student can correctly conclude that the hydrate, and this should say was, heated a sufficient number of times in the experiment. Okay, so we have our crucible. We dump a sample of our hydrate in there, and then we just heat it. And we heated it once, but after we heat it once, I mean, we lost some mass, which would be the water, which is what we're trying to do, but there's no way that I know if I lost all of it. So what I have to do is I have to heat it again. And so since I lost some more, maybe there's still some in there. So then I heat it again. And then I did not lose any more. So what that means is that between trials 2 and 3, because no mass was lost, all the water can be assumed to have been evaporated away. So here's how I'm going to phrase this. Just, goodness, no mass out. Okay, so that looks good. So we need to get the total grams of water lost when the sample was heated. There's plenty of ways to do this. What I'm going to do is I'm going to take 25.825 grams, and I'm going to minus 23.976 grams, because the only thing that happened between all of these is just water was lost. And so what I get is I get 1.849 grams of H2O lost. So I need to determine the formula of the hydrated compound. Here's how I'm thinking about this. MgCl2 is some amount of waters. We're going to heat it. We're going to get MgCl2 solid plus H2O. And I know the number, or the grams of H2O, 1.849 grams. I need to get this number. Again, plenty of ways to do that. Here's how I would do it. Is I would say, well, the only thing left here is this is just MgCl2 and your dish. So let's just subtract out the dish. And so when I take 23.976 grams minus the dish, 22.347 grams, that gives me 1.629 grams of MgCl2. Now I can do percent to mass, mass to moles, divide by the smallest. I don't have percents, I just have masses, so I'm going to start at step 2. I'm going to take 1.849 grams of water. There's 18.02 grams of water for every 1 mole of water. That gives me 0.1026 moles of H2O. Then I'm going to take 1.629 grams of MgCl2. There are 95.20 grams of MgCl2 for every 1 mole of MgCl2. It's going to give me 0.01711 moles of MgCl2. And then I need to divide by the smallest, which should always be my anhydrate. And when I do that, I get 5.996, and I get 1. And so because that's within a tenth for my waters, that'll be 6. My final answer is MgCl2 dot 6 H2Os. And then the last question in this video, and this one comes up a lot, is it says a different student heats the hydrate in an uncovered crucible and some of the solid spatters out of the crucible. This spattering will have what effect on the calculated mass of water lost by the hydrate? And so I'm not going to write the answer here. I'm just going to talk through it. And here's the whole basis of this lab. This lab is we're just going to heat our sample. Okay, we're going to just heat our sample. And in the process, we're going to lose some H2O, lose some H2O, and then we're going to heat until we have a constant mass, meaning no more water is lost. So if we have some spattering and some of our solid magnesium chloride spatters out of the crucible, we are going to assume that that is water being lost. And so what that'll do is that'll make it appear as though more water is lost than really is. This will lead, if you do the math, and you can prove it with math or you can talk through the math, this will lead to a calculation showing more water in the hydrated compound. Okay, so that'll be the type of answer you should have for part D.